Okay, so we're almost ready to start graphing our functions, but before we do that, we need to talk about limits at infinity, or how does our graph behave as x goes towards minus infinity or positive infinity. And so when we talk about this, potentially, we could come up with a horizontal asymptote. And you'll find a formal definition for this in section 3.5 of the text. But for now, we'll use this definition. It says the line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L. Or that is, as the function gets larger and larger and larger, instead of it increasing without bound or decreasing without bound, the function is going to taper off. Okay, the end behavior is going to be limited or maybe bounded by some number L. And so we actually talked about this in college algebra or pre-cal, where we looked at finding these horizontal asymptotes. And I actually just copied this from my Math 110 college algebra notes. So we're going to use these same rules to help us determine what the horizontal asymptotes of some of these functions might be. So first, it says when the degree of the numerator is the same as the degree of the denominator, the line y equals a over b is a horizontal asymptote where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. All right, so when we determine these horizontal asymptotes, what we're going to be looking at is the degree of the numerator and denominator, and we're also going to be using possibly those leading coefficients to help us determine what the horizontal asymptote is. In this first case, we've got three cases here. In this first case, we have the situation where the degree of the numerator is the same as the degree of the denominator, okay? And you'll see here in example A, that's exactly what we have. The degree of our numerator is 2, okay? The degree, of course, is determined by the highest powered term in that expression. So we only have one term here, and it has a power of 2, okay? So the degree of our numerator is 2, and the degree of the denominator is also 2. So the degrees are the same. The leading coefficient of our numerator is 3. The leading coefficient of our denominator is 6. So according to this rule, our horizontal asymptote is going to be the line y equals 3 over 6, or y equals 1/2. Okay, as this graph tapers off, when we get out towards the end, it's going to be bounded by the line y equals 1/2. Okay, the second case is when the degree of the numerator is less than the degree of the denominator, the x-axis, or the line y equals 0, is going to be the horizontal asymptote. And so when we look at this one, we've got f of x equals 2x over 3x cubed minus x squared. Okay, so the degree of our numerator is 1. The degree of the denominator is 3 because of our exponent here. It's the highest powered term, so that's going to be the degree of our denominator. And the rule says if the degree of the numerator, so we had 1 here, is less than the degree of the denominator, 3 here, then the x-axis, or the line y equals 0, is going to be our horizontal asymptote. All right? And then finally, it says when the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. All right? So when we look at this function, we've got f of x equals 6x cubed plus 4x over 3x squared minus x Okay, the degree of my numerator is 3. The degree of the denominator is 2. The degree of the numerator is larger than the degree or greater than the degree of our denominator. So we would say that there is no horizontal asymptote. Okay, no horizontal asymptote since the degree of the numerator is larger than the degree of our denominator. All right, so we're going to use these same rules again here to determine the limit. And notice here when we're looking at these limits, we're approaching infinity or minus infinity. And so when we do that, essentially what we're being asked to find is if there is a horizontal asymptote. Okay, so looking at A, we've got the limit of 3 minus 2x over 3x cubed minus 1 as x approaches infinity. Okay, I note that the degree of the numerator is going to be 1 and the degree of the denominator is 3. Okay, so since the degree of our numerator is smaller than the degree of the denominator according to the rules that we just had, we'll have a horizontal asymptote of y equals 0, or we can say that this limit is equal to 0. And this next one, when I look at the degree of the numerator and compare it to the degree of our denominator, I see that they have the same degree. So the horizontal asymptote in this case would be found by taking the ratio of the leading coefficients. All right, so that would be 5/4. So this limit would be 5/4. All right, and then finally, here we have one where the degree of our numerator is 4, the degree of our denominator is 2. So since the degree of our numerator is greater than the degree of our denominator, there is no horizontal asymptote. So I would say that this limit does not exist. Okay, let's take a look at another example. In this example, we want to look at the limit as x approaches negative infinity. Okay, and we've got x over the square root of x squared. We're going to try to use the theorem, I think it was 3.10, so that we can get things in the form where we have a constant in our numerator and then we have x to some positive power in our denominator, because we know the theorem. And let's go back and look at that just quickly here. The theorem says if we can write it that way, and maybe I didn't read this one yet. If r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r equals 0. Okay, and this is true even when x is less than 0. Okay, the limit as x approaches negative infinity for c over x to the r is equal to 0. So we want to try to get these things in a form where we have a constant over x to some positive power. If we can do that, we know that the limit's going to be 0, whether x is approaching infinity or x is approaching negative infinity. All right, we're interested in the limit as x approaches negative infinity of 5 over x minus x over 3. Okay, so if we go back and review some of our limit properties, we know that we can actually distribute a limit over a sum or difference. Okay, so that means we've got the limit as x approaches negative infinity of 5 over x minus the limit as x approaches negative infinity of x over 3. Okay, well, this first one is actually in the form of the theorem that we just looked at. Okay, we've got a constant over x to some power, and so according to that theorem, this limit is going to be 0. Okay, now for the other piece here, if we wanted to, we've got a constant times x. So we could actually bring that constant, 1/3, outside of our limit. Okay, so we got minus 1/3 times the limit of x as x approaches negative infinity. Well, if x is approaching negative infinity, which it tells us right here, then this thing is getting more and more and more and more negative. So what we end up with is something like 0 minus 1/3 times negative infinity. Even though the 1/3's there, since we're going towards negative infinity, this thing is going to keep decreasing, continue to decrease, except for the fact that we had a minus 1/3 times negative infinity, so the whole thing comes out to be positive infinity. Okay, so in this case, if we wanted to talk about a horizontal asymptote for this particular function, when we look at it, at what it's doing as we go towards negative infinity, there is no horizontal asymptote. Okay, let's take a look at B. In A, note that they had some help for us. We were already almost in that form, at least for one term, where we could say that the limit as x approached negative infinity was 0. If we're not already in that form, then we want to try to get as many terms as possible in that form or as a constant. And the way that we're going to do that is to, usually, we'll try to divide the numerator and denominator by the highest power that we have in the numerator or denominator. So in this case, both the numerator and denominator have a power of 2. So I'm going to divide top and bottom by x squared. And so when I do that, I've got the limit as x approaches negative infinity of 4x squared plus 5 over x squared, and then x squared plus 3 over x squared. Okay, we get the limit as x approaches negative infinity. Well, when I simplify, 4x squared over x squared is just 4, and then we get plus 5 over x squared. Okay, in our denominator, we do the same thing. X squared over x squared is 1 plus 3 over x squared. Okay, so now I can evaluate the limit of each of these terms. Okay, we could actually distribute the limit to the numerator and denominator, and we just mentioned we can also distribute the limit across a sum or a difference. So basically, I'm going to take the limit of each of these terms. Okay, so the limit as x approaches negative infinity of just 4 is 4. Okay, it doesn't matter what x is doing. If the function that we're looking at is 4, then it's going to remain 4, no matter how big or large x gets. Okay, then for this one, we can apply the theorem. Since we've got a constant in our numerator and we have x to a positive power in our denominator, we know that that limit is 0. And then we have the same situation in our denominator. We've got a constant here, so that's just going to be a 1. We have a constant over x to a positive power. That's 0, and so we end up with 4. Okay, so our limit as x approaches negative infinity for 4x squared plus 5 over x squared plus 3 is 4. All right, for C, I think we'll need a little more space. We're interested in the limit as x approaches negative infinity of x over the square root of x squared plus 1. Okay, now again, what we want to do is kind of consider or try to consider what the highest power is in the numerator and denominator altogether. Of course, we can see in our numerator, x is to the first degree, so that's fine. However, in our denominator, x is still to the first degree. Even though this is an x squared, we're taking the square root of it. So the highest power, really, for both the numerator and denominator is 1. So I'm going to divide the top and bottom by x to the first power or its equivalent. Now, what we have to pay attention to is the fact that x is approaching negative infinity. So in that case, what we can say is that x is equal to negative square root of x squared. Okay, I'm not going to just divide by x here because I've got my radical. I'm actually going to want to divide by the square root of x squared. But I'm approaching negative infinity. I'm going towards the negative number. So when I take the square root of x squared for x is less than 0, that thing has to be negative. Okay, so here we want to say x equals negative x squared. Now, if I was going towards positive infinity, then we would just say x equals positive x squared. But we're approaching the negative numbers. So that's why we have to do that way. So over here, when I divide, we're looking at the limit as x approaches negative infinity of x over x, okay, over the square root of x squared plus 1 over x, except I'm going to represent x as negative square root of x squared. Again, because we're approaching minus infinity. Okay, and so now I start to simplify this. X over x is just 1, so that's good. Okay, here I've got this negative. It's just going to come out front. And of course, because we have a radical over a quotient or two radicals over the quotient, we can combine them. So I can rewrite this as the square root of x squared plus 1 over x squared. All right, and when I distribute that x squared to each of the terms here, we get the limit as x approaches negative infinity of 1 over, and we'll put the negative out front now, this negative that was in our denominator. It's just going to be out front. So we got the square root of 1, because x squared over x squared is 1, plus 1 over x squared. Okay, and now we're getting somewhere. Okay, we got the limit as x approaches negative infinity, and really I think we're ready to evaluate because we've got our negative out front. Up top, of course, we know that limit is just going to be 1. In the denominator, we've got a constant there, so that limit is also 1. And using the theorem that we just talked about, we know that the limit of 1 over x squared is going to be 0. And so overall, this limit comes out to be negative 1. Okay, but the trick here is making sure if we're talking about taking an even root as x approaches negative infinity, then we have to have the negative answer. Remember, when we talk about, let's say x squared equals 4. Okay, well, if I take the square root of this, square root of both sides, we get x equals what? Plus or minus 2. Right? There are two answers to that. If I know that x is going towards minus infinity, then I don't need the plus answer. We know the answer is going to be negative 2. And that's what we're doing here. Because we know that our x is going towards minus infinity, then when we set these equivalent to one another, we get x equals negative square root of x squared. All right, let's take a look at the next one. Okay, this is D. And here we've got the limit as x approaches infinity of 5x squared plus 2 over the square root of x squared plus 3. Okay, so the numerator is really not a problem because right now, the way that it stands, I can evaluate the limit of this. Okay, if x is going towards infinity, this whole thing is going to keep getting larger, and this is just a constant. So infinity plus a constant, that's just going to keep getting bigger. Okay, but we need to do something with this. Okay, so what I'm going to do is actually factor out um, the square root of x squared. So we get the limit as x approaches infinity of 5x squared plus 2 over, I can write this as x squared times 1 plus 3 over x squared. Okay, because we just factored out x squared. Factor x squared from here, it leaves us with 1. And basically, we're dividing by x squared, so that's what I did there. You can see if we multiply back through, we'll get the same thing, x squared plus 3. And because I can distribute a radical over a product, then this is the limit as x approaches infinity of 5x squared plus 2 over the square root of x squared times the square root of 1 plus 3 over x squared. Now we've got the limit as x approaches infinity. Okay, and of course we know the square root of x squared is just x. So I'm going to actually move that to my numerator. I'm going to multiply by the reciprocal of that thing. So we got 5x squared over, or let's go ahead and say plus 2, and that's going to be over x. Okay, here we had just an x, but if I wanted to multiply by the reciprocal, let me kind of do it this way. We're multiplying by 1 over x. Okay, and so in my denominator, I still have the square root of 1 plus 3 over x squared. Okay, my denominator is good because we've got that form where we have a constant over x to some positive power. I know the limit of this thing as x approaches infinity is 0. The limit of 1 as x approaches infinity is just going to be 1. So we're good there. Now we need to manipulate our numerator a little bit and just really simplify. Okay, 5x squared over x is 5x plus 2 over x. Okay, we still have our square root of 1 plus 3 over x squared. Okay, so when I evaluate the limit as x approaches infinity of 5x is infinity. The limit as x approaches infinity of 2 over x is 0. And we already said the limit as x approaches infinity of our denominator is just 1 because we got 1 here and we have 0 here. Okay, so then the whole thing comes up to infinity. Okay, this one does not have a horizontal asymptote. As x continues to get larger and larger and larger, the function will also continue to increase without bound. All right, so for this one, again, we've got x approaching negative infinity, and we've got the square root of x to the 4th minus 1 over x cubed minus 1. All right, take a minute and decide what the highest degree of this overall expression is going to be. And hopefully you have decided that the highest degree is x cubed. Okay, we have x cubed in our denominator, and in the numerator we have the square root of x to the 4th, which might be x squared. Okay, so that's a lower degree. However, since we're going towards negative infinity, I want to remind myself that x cubed is going to be equal to negative square root of x to the 6th power. Okay, of course, the square root of x to the 6th power is plus or minus x cubed. But because we're going towards minus infinity, we're going to use the negative value of this. And this is true because we're looking or approaching x values that are less than 0. Okay, we want to know what happens on that end of the number line. So now that I have that, I'm going to divide top and bottom by x cubed, or the appropriate equivalent. So we got the square root of, or x, the limit as x approaches negative infinity. Okay, and I've got the square root of x to the 4th minus 1 over negative square root of x to the 6th. Okay, and we're going to divide that by x cubed minus 1 over x cubed. Okay. And so we've got the limit as x approaches negative infinity of negative square root x to the 4th minus 1 over x to the 6th. Okay, we're going to deal with that in just a minute. Okay, and then we also have in our denominator, if I distribute the x cubed, it's going to be 1 minus 1 over x cubed. Okay, and we know that that's a good thing because we know the limit of 1 and we know that the limit of this thing is 0. Okay, so we just need to do something with our numerator for right now. And so we got the limit as x approaches negative infinity. Okay, if I distribute x to the 6th to each of these terms, then I'm going to have the square root of 1 over x squared. Okay, that's a good thing because I know the limit of this thing is 0. And then minus 1 over x to the 6th. The limit of that is also 0. So I can evaluate the limit of each term that I have in this expression. Okay, and so if that's the case, we already said the limit of each of these is 0. Square root of 0 is 0. The negative no longer matters. On the bottom, we're going to get 1 minus 0. So the overall limit as x approaches negative infinity for this one is, all right, let's take a look at just a couple more. Okay, here we're interested in the limit as x approaches infinity of cosine of 1 over x. Okay, and it says recall that the limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x. And we've actually already been using that because we've had some expressions inside of a radical. And basically we evaluated the limit of the things that was inside of the radical. Let me back up here so we can see that. We've done that several times, but I've been focusing on evaluating these limits instead of doing the radical first. We can kind of move that limit inside of the radical expression and then take the radical. So we found that this was 0, and then the square root of 0 is 0. So we've been doing that already. So let's do it again. If we're interested in the limit as x approaches infinity of cosine of 1 over x, okay, that's equal to cosine of the limit as x approaches infinity of 1 over x. And of course, we know that the limit as x approaches infinity of 1 over x is 0. So we can look at cosine of 0. And we know cosine of 0 is equal to 1. All right, and then finally, we've got the limit as x approaches infinity of x minus cosine of x divided by x. Okay, so what I'm going to do is distribute that x Okay, and we're taking the limit of all of this. All right, of course, x over x is just 1. And we still have cosine x over x. Okay, I can distribute the limit across a sum or a difference. Okay, so we got the limit as x approaches infinity of 1 minus the limit as x approaches infinity of cosine x over x. Okay, well, if you'll recall from earlier in the semester, we had two special trig limits, and this was one of those limits. And what we found was that the limit as x approaches infinity of cosine x over x is equal to 0. Of course, the limit as x approaches infinity of 1 is just 1, so we get 1 minus 0, or just 1. This takes a little practice, but if you'll, work on it and try to use these principles, work on the homework in WebAssign and additional problems from the textbook, I'm sure that you can understand this concept.